Let's go on to our next speaker. And we have Dr. Amir Sadeghpour. He's an associate professor at the School of Ag Sciences at Southern Illinois University, Carbondale. Dr. Sadeghpour is a leading SIUC soil management and integrated cropping systems lab, and his research and teaching program focuses on improving farm profitability and resiliency through integrating precision nutrient management principles. Amir earned a PhD from the University of Massachusetts in plant and soil sciences in 2014. Prior to moving to SIUC, he was a postdoctoral fellow at Virginia Tech and Cornell University. Let's welcome Amir Sadeghpour.
Thank you for that introduction. Today I'm here to present on two of our NREC projects. One of them being precision nitrogen management of corn, and then the other one is next generation of cover cropping. As you can see, there are lots of people involved, so I'd like to thank each and every one of them, and also thank Illinois NREC for funding our project and make this happen. The objective of this project is to give growers an alternative or another option for nitrogen management as compared to MRCM. This project started in 2018 by Josh McGrath at the University of Kentucky at the time. Basically, the design of the study is having basically 5 started nitrogen rates, splitting into 2 subplots, and then half of those received no fertilizer and the rest received those side race nitrate, basically nitrogen levels. And that's kind of like how that looked like. In 2019, Illinois NREC started funding our project, and so we changed that design of the study to having 4-way splits, meaning we had no side dress rates, starter only, starter plus side dress, and then a starter plus max side dress. That was like high enough that we know there would be no end limitation. We also included a range of starter fertilizer rates, going from basically that starter fertilizer plus those rates all the way to 315 or something like that, and then splitting those with that max nitrogen rate being 577. So we had like rates that go to crazy really high to just make sure there will be no limitation whatsoever. This would help us with 2 things. One, building that algorithm to predicting nitrogen yield, it's really helpful to have those upfront nitrogen rates, and 2, allow us to compare side dress application with starter application, with upfront nitrogen application. In 2020, we kind of reached a uniformity of like, okay, these are the rates that we're going to use, and we're going to keep going with them. This is an example of one of the fields that we have. Those are how those 4-way splits look like in the field. And then within that field, and this happened a couple times, that we had fields that are large enough that would give us like around 2,000 plots in one field. And this is one of them. Overall, over these years, we ended up having basically 130 nitrogen rates tested, and then ranging from 0 to 577 pounds per acre. From 2018 to 2020, we had around like 70,000 data points, and then from 2021 to 2023, we added another 12,000 data points. So overall, it's like something like 19,000 data points that we have. And then as of 2022, we have 64 site year cover timing. Those are like with cover crops included in some of those trials. So basically, that would allow us to So basically you have what are the starter considerations for Illinois, Southern Illinois, and then what are the side risk considerations for Southern Illinois, and then can we build a variable rate nitrogen application and capture spatial variability within the field. Some of our data, this is lots of basically data. On the x-axis is the bushel per acre of corn yield. On the y-axis is percent of occurrence of those yields. And then you can see the yellow color is yield without nitrogen, and the blue color is yield with nitrogen. And you can see lots of high yield even without adding any nitrogen existed. Our agronomic findings basically show that we needed 37 to 55 pounds of starter fertilizer. So if you're managing in, that's something that is needed. And then our yields, and then being on average 214 bushel per acre, and needing an optimum nitrogen rate of 216 pounds per acre. So that would kind of be close to that 1 pound per 1 bushel. That is generally a rule of thumb. The current, basically, Kentucky recommendations suggest 185 pounds of nitrogen per acre. In MRTN for Southern Illinois, the last time I checked, range between 180 to 205 pounds per acre, which is on average 195 pounds per acre. That response that you can see, however, is coming out of this craziness. And that suggests that yield is spatially variable. So that's what we are trying to capture. And we know that basically nitrogen fertilizer is a function of yield responsiveness and then basically yield potential. And what we are seeing here, having yield without nitrogen regress with yield with nitrogen, which is clearly related. And then delta yield, meaning yield with nitrogen minus basically yield without, as compared to basically responsiveness. Both are related, but when we look at the yield without nitrogen versus yield response is not related. That suggests that we should kind of move away from empirical nitrogen recommendations and capture the variability that exists. That suggests its end recommendations are site-specific. So for each year in each location, we need to figure those out. That made us developing this algorithm. So basically the way the algorithm works, or we develop it, is by creating response index, which is having NDVI and yield of high nitrogen rate versus the low N, and then creating those response basically equations to predict yield at high N versus yield that is low N, and then capture the difference between the two to prescribe a nitrogen recommendation. And that kind of works this way. So you usually have low, if you have basically in the middle of that, does this work? If you're in the middle of, in that equation, you apply your maximum nitrogen. That means that you get the highest return. If you're lower or if you're higher, you won't probably get as much return, so you decrease the N basically applications. So this is a map of one of our site years. This is in ARC in Carbondale, and in 2022, the numbers there are nitrogen applied. The color coding is the yield map, basically. So those yield ranges that's shown in the legend, and then those stars and basically triangles are placement of whether we have chambers for measuring gas emissions or lysimeters placed into the field. The only thing that I have to suggest that is that like that 187 pounds per acre that has a star received extra nitrogen so that we have 204 pounds of N, so that we have upfront nitrogen application and citrus application being the same rate, so we can compare apple to apple. So the data that we found in terms of like a nitrate, a soil nitrogen trend, and this is nitrate nitrogen. So we have 3 treatments that we tracked across the growing season that year. No nitrogen, that green sickle algorithm. And I forgot to mention that actually those blue boxes are strips of green sickle algorithm or sensor-based algorithm that then applied, that basically went at V6, V7 sense and then give us like a prescription, and we applied based on that. That's to test what we are finding. So that GS is that algorithm-based basically nitrogen, and the MRTN is that 204 pounds per acre. That is upfront applied. And then you can see that basically soil nitrogen increasing over time, and then being low with just 55 pounds of a starter fertilizer with the green sickle first, and then getting some peaks when we side dress those rates. And then as the corn grows, you can see that nitrogen decline over time. This is the soil moisture that we had in that trial, initially being higher, and then as the time goes by, that soil moisture usually declines. We get in that green box, we get like a heavy rainfall event, so you get a jump again in the soil moisture and then decline again. When we looked at soil nitrous oxide emission for those treatments, you can see that most of the action happened in that basically early time of the season, and then once we side dress, we get a heavy rainfall event, we get another kind of peak which was smaller. And that's like, usually these nitrous oxide data for the rest of it is very boring. So not much happening when the corn is taking up a lot of nitrogen. So this is our cumulative nitrous oxide emission data. So we have a trend from being highest in MRTN, then followed by green sickle algorithm, and then being the lowest with the no nitrogen. The yield at the MRTN, that's average of basically side dress and upfront application, was 173 bushel per acre. The yield at the basically green sickle was 162 bushel per acre. And that shows that we get, on average, 11 bushel yield penalty there. But we also use 204 pounds of nitrogen in the MRTN, and then we only use 78 pounds of nitrogen based on that green sickle algorithm. When I put two basically economic scenarios with corn price and nitrogen fertilizer price, in both situations, the green sickle is basically having higher return, not considering the cost of variable application. For the leaching data, we had resin lysimeters in all like plots of MRTN side dress and basically MRTN up front. So I'm separating them, and then you can see that we get higher yields with MRTN side dress application than basically upfront. We're talking about 178 bushel per acre versus 168 bushel per acre. But what is striking and wild is that reduction in soil and basically nitrate leaching. This is like 3-fold lower at least. And I think this is beyond the goal of Illinois nutrient loss reduction strategy. So if we can figure this out, I think that single-handedly is helping to basically cover that reduction. This time, with having side dress MRTN having higher yield, in the red economic scenario, still is not catching up to the variable rate nitrogen management, but in the green scenario, it does. So we have still work to do, but that's pretty, I think, exciting and interesting. We've been seeing this constantly. The moment you pass the optimum nitrogen rate or a rate that is beyond 200 pounds per acre, you see these pockets of high end of season N. These are deep core samples like Joel was showing. And then, so these are contributing to N losses that would occur off season. But those can be captured. So within that ARC field that I just showed you, the map, we went and planted wheat all across it. And then we looked at wheat biomass when we have it as a cover crop, no nitrogen applied whatsoever. Whatever's there is whatever coming from basically residual nitrogen from those nitrogen application rates. And then we saw that like there is a linear relationship between end of season N and applied with basically biomass of wheat. When we let that wheat go to basically bushel per acre, that actually become exponential, meaning later it actually grow and capture a lot more N and become like, we got something like a 60 bushel per acre wheat with no nitrogen applied in those higher N rates. So to kind of wrap this first one up is that I think it's critical to capture environmental economic risks associated with year-to-year variability that we have. A precision nitrogen management can help as a strategy that estimate in season basically yield to cope with that variability. We have a draft algorithm, that's the one that we tested, and it seems it's showing some promise in reducing nitrogen losses and potentially improving farm profitability. We were talking with Josh McGrath. He said this happened to him when he was making an algorithm for Maryland, that we couldn't match the yield of variable rate with the flat nitrogen application. But he said that by tweaking it, and we should be able to match that yield using your data, and then hopefully providing a basically tool that is not costing growers yield penalty. We don't know what will happen once we do that in that nitrate leaching and N2O emissions by doing that. That's that. And then we have another project that's next generation of cover cropping. Again, lots of people involved, and I'm really grateful to all of them. This is doing with SIU and University of Illinois. Taylor's here, and that's her project, kind of. And then with Andrew Margionot being the PI at U of I. Whenever we talk about cover crops and cover crop management, we usually think about 5 of those managements, like right species, seeding date, seeding rate, and then planting methods and termination date. And what we are really focused on here is that precision planting. What do I mean by that? As Shalimar talked a lot about it when he was giving a talk, is the goal is to minimize intersecting zones of those cover crops with the cash crop. Meaning, if you can see here, every corn is 30 inch apart, every cover crop will sit 7.5 inch, and you have 2 rows that are intersecting with your corn in rotation. The goal is to eliminate those or place something that is like more friendly, like a legume on those rows. One of the studies we did, that was like a pilot study that we did first to get that funding from you guys. And then we did it in 5 side years. The goal was to see whether by doing this precision planting, are we getting the same benefits? Are we giving the same biomass in rye? How is the basically temperature on the corn row changes? Is the C to N ratio of that cover crop is different from normal planting versus precision planting, and would that influence corn yield? So what we found is that the biomass was completely the same. That's that figure. The soil temperature on the row of the corn row was warmer, which helps with germination, which will allow for a little bit quicker growth early in the season. The C/1 ratio was the same, and then one thing we saw that in the corn yield, in 3 of those ARC sites, we never saw any yield penalty and then improvement of doing precision planting compared to normal planting. Whenever we didn't have the capacity to do 2x2 starter fertilizer in those BRC fields, we saw a yield penalty compared to the fallow treatments. So that's like talking about how important it is to do 2x2 fertilization, especially with the cover crop systems. The second study that we had, we looked at basically precision planting with winter wheat and with different termination dates. So we looked at basically early termination, late termination, and we removed the residue. One of the interesting things that we saw was that whenever we took biomass samples early in the season, there was no difference between those 2 treatments of precision planting versus normal planting. But whenever we went and let it go further away, we saw some basically lower biomass with precision planting. When we look at the corn yield, interestingly, if you look at those 2 red colors, those are when we remove the wheat residue, and we get a severe yield penalty in that year. And we think that when you cut the wheat and if you go and plant into it, it starts to basically give root exudates, allelopathic compounds that would influence the population of corn in a manner that you cannot overcome it with any nitrogen fertilization. Interestingly, though, that precision planting, which is this one, helped with that, but couldn't completely solve the problem. In a different study, we tried to basically place clover on the corn rows and then compare that with the normal clover rye mixtures, and then also compare precision planting of clover versus normal planting of clover, which we didn't have any data for. So this is done for 3 years, and then one thing we found is that in the year 1, as you go from clover all the way to having more rye in the system, you're seeing increase in biomass. And then in the 2 other years, you're seeing low clover basically establishment. It's been a little bit challenging to establish clover to the point that you want. The difference between those 2001 versus 2022 and 2023 was that the first one went after soybean. The 2 other ones went after corn. And it seems like it's much easier to go after soybean and plant it versus corn. That basically, this was like a very multi-state project, and they wanted to go corn after corn to test for nitrogen recommendation for corn. And average over 6 nitrogen rates. So we got a response of basically cover crops by year interaction. And then you can see that the clover ones always yielding higher. Those yields are low because they're average of 6 nitrogen rates. But then that clover benefit, in at least in those 3 years, kind of disappeared when we get to that optimum nitrogen rate for them, which I think is one of the challenges that we should try to figure out to give credit to these clover and legumes, basically. And last one is that long-term study that Taylor is managing in University of Illinois with Andrew Marganot, and then we are managing it. And that's our site, that drone image. You can see we have 5 basically replications there, 11 treatments for us. And then those treatments range from inner seeding these rye clover mixtures all the way to having cash crops like malting barley and wheat in there. And then one thing that we saw when we started this project, we started from the corn phase, and then so we went and inner seeded into the corn. We get a stand establishment of basically rye and clover initially, but those disappeared like within a month. After we get that August drought condition, we didn't have like rain for like 20 days. Interestingly though, when we went to the soybean the year after that, and we planted those basically cover crops after leaf drop of soybean, we got a really good stand. So that figure shows basically clover stand later on with early and late termination. That actually worked pretty well with inner seeding. So it can work, but it's like a little bit tricky. A lot easier to go into soybean and a lot harder to go into corn. And I think that's what we really need, is to go into soybean so that we have clover establishment for the corn, that when you go plant into the corn, you have those clovers to benefit from. That was, and I think that was the last thing that I want to mention, is that this nitrate leaching that you have here, that's all pure variability. There was no treatment except that inner seeding was imposed in that very initial baseline year. So you can see that there is a lot of spatial variability in nitrate leaching in a field that we should capture. In basically, when we went to the cover crop phase after that, we are seeing a reduction, at least number-wise, compared to the fallow treatments with cover cropping. And no matter if you had a lot of biomass and you have just 1,000 pounds, it helped. And then when we went to soybean phase, and that exists as well. So what we found so far is that precision planting seems to be working, helping with minimizing yield drag, especially in winter cereals. Basically, I think it's pretty important to understand how we mix these cover crops to get the most out of them, especially if you want to have more clovers in the system, finding those ratios that we mix to allow clovers to kind of compete with rye in the system. Also, it's pretty important to know that basically how do we credit these cover crops for the end use in the system, especially in the corn cropping systems. And then eventually, we talked this with Andrew Marganot some, like, can we use our existing data and the data we are capturing to find like carbon crediting with these cover crop management systems, which requires all the inputs of the carbon and all the outputs, like measuring nitrous oxide emissions, CO2, and methane within those systems to account for a sustainable management approach. With that, I would like to thank you, and if you have questions, more than happy to do it.
On the sensor-based applications, what was the timing and what was the low end of the rate and the high end of the rate during that application? So
for it, if you had seen that, it was very stable. So we didn't go. If you can see those numbers, the timing was around like V7 to V8 of corn, but whatever that sensor gave us, it was very stable. So it didn't give us like 160 something and then 20 something. It gave something around like 70 to 90 pounds per acre.
So it didn't vary, wasn't much variability within that square?
No.
Was there any ammoniated phosphate applied ahead of any of these trials?
No. So it was all UAN 32%. No, correct.
So In this study where you compared the MRNT to the green seeker, the N rate, was this at one site or multiple sites or one year?
We have 6 by now. So it's been like going on, but from the time that we built that algorithm and we start testing it, we have 6 site years.
Okay, so the yield
This-
data and economics data was from 6 site years?
This was for this one only.
Okay,
We have, so average yield penalty for all those combined was 8.6 bushel per acre.
All right, thank you.
Of course. That was 2 by 2 like placement. Yes, correct.
Do you know how to get a hold of Odie?
Where I live in Illinois, crimson clovers may be annual, so when you planted that, you actually saw enough growth to have some nice vegetation.
We did. So it depends on timing. So it's been like with those legumes, timing's been the key. So I have a student, Golchin, and with her study, she's working with sweet corn. And sweet corn you harvested a lot earlier. So we have time to go and plant on time. It's like she has a beautiful field. But then with corn, you get to harvest, getting to October, and then you go plant it. It's a lot harder to get high biomass. That year, the first year, it was soybean. They told us like, you gotta go ahead and plant this as soon as possible. We went, cut the soybean out. They didn't want us to kill the soybean. They wanted to take it out so we don't get much residue that is like high end to the system. But we planted that like September 24th, something like that, versus October 15th or something. So anytime we planted like close to end of September, we get a really good stand. Anytime we went to like October 18th or October 15th, that's become challenging to establish.